Hello and welcome to lecture number 2 of 4017, the course on photorealistic and non-photorealistic rendering. So in today's episode, we're going to cover raycasting along with a brief review of some of the math that we need for raycasting, but not only that, for ray tracing and our non-photorealistic rendering that will happen later in the course. So just a few announcements. First, assignment 1 is posted, so please make sure that you take a look at that. It's due, I believe, in a couple weeks, and you're going to be needing to do a little bit of Python programming for that. So if you have any questions when you're going through the assignment, make sure that you send me an email right away and we'll get you all sorted out. The other thing I wanted to mention is that we'll be doing a Python refresher. I'll post that on Brightspace as well, so that for those of you who have not done Python in a while, you can review those ideas. So what we're going to do today is, in our last lecture, we looked at some really cool photorealistic images that were so real you probably thought they were a photo. They weren't. They were completely computer generated, and that generation does a lot of math behind the scenes. And what's interesting is, on the flip side, we also looked at some non-photorealistic rendered images where we were making the computer do things that looked like human artworks, and there's a lot of math that's going on behind the scenes there as well. So what I want to do today is we're going to start with a very brief math review of some of the very key components that we're going to be using throughout the course, and then we're going to dive into raycasting, which is the first step of our rendering journey. So let's get started then. So just to give you a brief list here of the different math that we're going to review, we're going to start with the simplest one, which is the dot product, which I'm sure many of you remember. But let's just say we have a vector. So we have our vector, and we usually put a little arrow on the top of it to say, hey, this is a vector, but you don't have to do that. It's just, if you're reading anything, you might see it in that form. So if we have two vectors, u and v, so let's say u is a, b, c, and I apologize, this writing may not be very neat, but I'm using one of these lovely things here, and there's a little bit of a mental disjoint because you're not actually writing on the surface that you're looking at. So I've got these two vectors, u and v, and then the dot product of them is written like so, u dot v, and it is equal to ax plus by plus cz. So we are doing the pairwise multiplication. So we do a times x plus b times y plus c times z. So it's the pairwise multiplications, and then we add them all up, and that's how you get the dot product. And this is something that you are going to see everywhere. You're going to see it when we're trying to compute ray directions. You're going to see it when we're doing lighting equations. You're going to see it when you do shaders. This is a piece of math that is pervasive throughout computer graphics. We couldn't live without it. All right. So the next thing on our list then is matrix multiplication, because this is, again, one of those things that is everywhere in computer graphics. It's how we apply transformations, like scales and transform, or translations. And it's how everything is done with a matrix. So remember that a matrix is kind of represented like this. And I'm going to just use 2 by 2 matrices because that's going to be easiest here. So I've got matrix A, and we'll set its values equal to A, B, C, and D. And then we'll have matrix B, which will have values U, V, W, and X. Okay, so if we went to multiply these two matrices together, we would just write it like so. You don't need to put any operator between them. It's implicit. And what we're going to do, so this would look like this if we expand it. what we're going to do is we start by taking the first row and multiplying it by the first column. So what we're going to get is, well, we're actually doing the dot product of that row in this column. So we're going to get AU plus BW. And then to get the upper left, or the upper right one here, we're going to take the first row and multiply it by the second column. So what we're doing is we're taking the dot product of the rows and the columns of these two matrices. So let's fill in the rest of it. We get AV plus BX, and then we get CU plus DW, and then CV plus DX. So that's A times B. Now, one thing we get in regular math, which is just regular numbers, is the idea that 4 times 5, which we all know is equal to 20, is also equal to 5 times 4. And I want to tell you this right now, this is not true for matrices. And it's really important to know that, because when we're trying to put a bunch of rotations and translations and scales together, we might think that R times S times T, so rotation times scale times translation, is the same as S times R times T. And the answer is no, it's not. And I'd like to demonstrate that this is not, in fact, true. So let's grab this program I'm using here. It's very easy to lose my little dot. Yeah, see, I've lost my dot there. All right, so let's do B times A. So if we do this out, we get UVWX times ABCD. And that's going to give us AU plus CV, BU plus DV, AW plus CX, and BW plus DX. And if we take a close look here, what we see, comparing this element to this element, is that they're not the same. We have the AU component, but the second part, BW, is not equal to CV. So you can see here, this property of AB be equal to BA does not work for matrices. So make sure that you're multiplying things in the order that you mean to, because it is not equal otherwise. All right. So what's next on the list? We've got distance and vector length. So distance, let's go back to our other color here. So the distance between 2 points, so if we have point P, and if I have point Q, then the distance L, which is the length between them, is the square root of a minus x squared plus b minus y squared plus c minus z squared. Okay? And so that's distance. Now if I want to know the length of a vector, well, in order to use the formula above, we need a second point. So the second point we use is center, which is 0, 0, 0. So what we would end up with for some vector v equal to x, y, z is you end up with x minus 0 squared plus y minus 0 squared plus z minus 0 squared. That's pretty nice. But we can simplify this more. So what we actually end up with is x squared plus y squared plus z squared. And if I look at that, I realize, wait a minute, that's just the dot product of the vector with itself. So when we're doing vector length, it's equal to the square root of the dot product of the vector with itself. And that's a pretty useful little formula to have on hand. The next thing we want to look at on our list is something called normalization. Whenever you're doing any kind of rendering application, the direction vector is always given normalized. And what normalized means, in this case, is that the vector has a unit length, or its length is 1. And so what we want to do is we want to take some vector v, x, y, z, and we want to turn it into something of unit length. And how we do that is we say v prime, our normalized vector, is equal to the original vector divided by, and how you will see it usually written is something like this. And what this symbol here means is the length. So this is equal to v divided by the square root of v dot v. So what we're going to end up with is v prime is equal to x over x squared plus y squared plus z squared square root y over the square root of x squared plus y squared plus z squared z. So that will give us our normalized vector. And you're going to see normalization everywhere. So when we make the original ray vector that goes from the eye into the image, we're going to take that direction vector and we're going to normalize it. When we create the surface normals, we're going to normalize them because these formulas work with vectors that have unit length. Now, the last little bit of math I want to review is something that you may have heard of before, or maybe you have not heard of before, but it's this concept of rounding and epsilons. So what we have on a computer is a limited ability to represent numbers. It can only store so many digits in memory. And the problem is numbers like pi have, as far as we know, an infinite number of digits. And pi, as you probably guessed, shows up a lot in computer graphics because of circles and spheres and things like that. And so on the computer, since we can't represent all those digits, we end up rounding or truncating them. And what happens is, because we're constantly rounding or truncating those digits, we're using imprecise math. And every time we add, subtract, multiply, or divide, but especially multiply and divide with these numbers that have been rounded, we are increasing the amount of error that is introduced into the system. So on paper, you might have an equation that works out perfectly to equal 0, and then you take it over to the computer and you say, okay, if this equals 0, then do this following thing, and it never happens. And you're sitting there like, I don't understand what's going on. Well, the reason is because when you do all that math on paper, you're usually using just the symbol pi to represent pi, whereas on the computer, it's using an estimate of pi, and hence error gets introduced, and so that 0 isn't really 0, it's some value close to 0. So we have this concept of an epsilon. It's some small value that we use to say, are you within epsilon of 0? Because if so, we're going to pretend it is 0. And you'll see that anytime we're doing some kind of comparison, we won't check to, is this 0? We will say, is this within epsilon of 0? And in the sample code we provide you for assignment 1, and in many different rendering applications, you will see these epsilons. You can actually edit them and play with them yourself. Because if you make the epsilon value smaller, it's going to mean it's a bit more precise, but more susceptible to error. And if you make it too big, then saying whether an array intersects an object, well, you might not be doing a perfect job of it. But you don't have to worry about the rounding error so much. So it's really a trade-off there. All right. So now that we've gotten that math bit out of the way, we can now talk about the concept of raycasting, which is the beginning of our rendering journey. Now, what raycasting is, and you might remember it from one of your previous courses, is it's really just a simple rendering of the scene where we are sending rays of light from the camera into the scene to see what can you see. So can you actually see an object, or do you see nothing? It is highly simplistic. So there's no reflections, there's no shadows, there's no refraction, there's none of those things at all. It's just saying, what is the color of the object you intersected when you sent the ray into the world? So we use ray casting to determine the visibility of objects in the scene. It really is the first stage of ray tracing. We can also use ray casting for many things, and we'll talk about that later. The one thing I really want to point out and emphasize here is that we are tracing light in reverse. So we are going backwards. Light does not magically shoot out of our eyes into the world. The world is shooting light into our eyes. So this is a bit of a backwards notion that we have here. So let's just have this diagram here to show you what we mean by ray casting. So you're going to have a camera or an eye, and if you're looking at any kind of rendering application, what you'll see is sometimes you can use a camera, or sometimes they'll refer to it as the eye. And we're going to shoot these imaginary light rays out of that camera through a pixel in our image, which sits somewhere in front of that camera. And what we're going to do then is, as it goes through the pixel of the image and into the scene, we are going to check which object is visible from that ray of light. And we are going to have to ask every single object in the scene, does this ray of light intersect you? And if it does, we don't just, well, what if you intersect multiple things? Well, you can think of it like this. If you've got a bunch of objects, so I've got this Wacom here, and then I've got this little light remote here. This light remote is completely occluded by the Wacom tablet. So even though my ray coming from my camera through this tablet would technically intersect both objects, I don't care about this object that's hidden behind because it's not visible. So we're checking for visibility. What can you see? What is the first thing you would intersect when you go into the world? And that's the color that we're going to make that pixel equal to. So if we were to take a lovely 3D dragon model, which you'll see if you've read any rendering papers, you'll see these models all over the place. If we were to raycast this, and I actually did this in Houdini, there's some settings you can turn on to make it so that none of the lighting equations are actually being performed. It's just the first cast. This is what you'd get. So I have a dragon with a white material, a floor with a red material, and then no background. So the rays go through, they intersect the object, they just return that base color. So I get this lovely picture here, which is actually kind of cool on its own, but certainly not what we were expecting. So if we ray trace this object instead, this is what we would get. Now you can actually see the surface detail to this 3D model. And the reason you can see the surface detail here is because I'm not just returning the color of the object, I'm actually performing a lighting equation. I'm checking to see how visible is this particular point on the surface of this object to the lights in the scene, and I'm performing a special set of formulas to compute how much light is being contributed to the color here. And I'm also doing things like looking for shadows, and I might be performing reflections and refractions. So this is ray tracing, where we get all of the nice surface details. Ray casting, we get none of it because we're not doing any lighting whatsoever. We're just checking for visibility. But this here really is the first step to this, because we can't compute the color if we don't know what object we've actually touched. And we'll be talking more about the tracing side of the world in the next lecture. So before we can get into the algorithm for ray casting in any kind of detail, there's a bunch more math that we need to talk about, because it's going to show up in shaders, it's going to show up in Houdini and Maya. You're going to see this. And the first one is this concept of the homogeneous coordinate system. This might be something you've seen before, and maybe it's not, but this is the coordinate system that we're using for projective geometry. So you've seen the Cartesian plane where you have an X and a Y, and when we're working with images in non-photorealistic rendering, we're going to be using X and Y. when we're working with 3D rendering, we have X, Y, and of course Z for depth. What we're going to do now is add a fourth point. Now, it's not something you can visualize. We're calling this special fourth point, it's the point of infinity. And what it means to us is it gives us a way to differentiate between vectors and points. So for a vector, the point of infinity, the fourth component is a 0. Because we don't have the, and this is going to be important when we're doing translation, because we don't have the ability to, we don't translate direction vectors around. A direction is just like this. A direction here like this is not, is the same as a direction over here like this. So we don't want translations to be applied to vectors themselves. But we do want the ability to translate a point, because that is a physical thing we want to be able to move around. So the point of infinity, the fourth component for a point, is going to be 1, and this is going to come into play when we do the affine transforms. Now, in some rendering applications, you may see the homogeneous coordinate, that fourth point, and you may not. But regardless of whether you see it, it's there. It's very much there. It's hiding. All right. So if we take a look at Houdini, where it does its translations, rotations, and scales, you can see here that they are not showing the homogeneous coordinate. A lot of applications aren't going to show it to you by default, because if you've never heard of it, you may be like, what's this fourth component? What happens if I change it? And you shouldn't change it, because you will change the very meaning of what you're doing. But it is hidden and there, just not maybe visible to you. All right. So now what we need to look at is the concept of affine transformations, because they're very important, not just to the ability to send rays out into the world, but it's also how we are positioning things in the world, how we are making them shaped. So are we squashing them? Are we rotating them? And so on. And the first of these is translation. Now, because we are using a homogeneous coordinate system, our matrix is a 4x4. And the translation component is in the final column. So the translation matrix has ones along the diagonal, and then in the final column we have the X translation, the Y translation, and the Z translation. So if we were to multiply a point by this, we would get the effect of moving that point in space. Let's actually do that now. So I'm going to create a new page. And so what we have here is, so our translation matrix, again, I apologize, I'm not the neatest writer with these devices. So then we have X, Y, and Z, where X, Y, and Z is the amount along the corresponding axis that we want to move the point by. When we multiply a point by a matrix, i.e. to move the point, we lay it down like this. And then we're going to perform the multiplication. So we are going to multiply the first row by the first column. And that's going to give us the first element up here. So this actually becomes A plus dx. Oh, my apologies, d. This is why we have the homogeneous coordinate system, is because when we have a point, the d component is equal to 1, so that dx there is actually just x. So a plus x. I have translated point A, which was that, or the x coordinate A, is now a plus x. And then I can continue this, so now I'm going to do the second row times this column. So I get b plus y and c plus z, and then we get 1. There we go. So that's how that point of infinity helped us perform this translation. And that is how I got this result right here. So if P is the point ABC and this is our translation matrix, that is the translated point. All right. Now, obviously, when we are doing this inside of a tool like Maya or 3D Studio or Blender, if that's what you like to use, what we're going to see, we're not going to be sitting there doing the computation ourselves. We have the ability to, either through these lovely handles here, to physically just move the object around, or we can type the exact amount we want to translate it to in these boxes up here. So if I set one of these boxes to a different value from right here, you can see here I've moved along the x-axis 1 full unit. And we can just open this up. And let's, I already have a scene open here, so I'm looking through this scene. I'm going to touch one of these apples. And what you can see here is I can now actually move it up, and watch when I move it, I'm moving it up along the y-axis. You can see the y-axis element of the translation component is changing. So that's what we're doing there. And this is probably how you'll be interacting with things. Now, if you wanted to create a shader where you were translating things, you would probably actually have to do that multiplication yourself. Now, of course, many rendering APIs, that is the libraries, the set of tools we have available to us, will already have a function for multiplying a matrix by a point. And so we don't actually have to, manually implement that ourselves. All right, so the next one is a big one. It's the rotational matrices. So we usually represent the angle, the number of degrees we want to rotate by, with theta. And there is a different matrix to represent each of the different rotational transforms. So if we want to rotate along the x-axis, this here is the matrix that we would use. And if we want to rotate along the y-axis, this is the matrix we would use. And then this is the one for the z-axis. Now, where is the x, the y, and the z-axis? Ooh, that's an interesting thing that we should mention. Every rendering application out there may have a different concept of where X, Y, and Z are. They might be left-handed or they might be right-handed, and that's just saying which way is up for each of the axes. So this here is the left-handed coordinate system, and we have Y up is positive, X positive is to the right, and Z positive comes out of the screen. Whereas a right-handed coordinate system has the Y going up, Z coming out, and positive X going to the left. And this is something to keep in mind, because I think most people think of the coordinate system on the left-handed side, but some applications use a right-handed coordinate system, and so if you're rotating, you might be rotating in a direction that is not what you're expecting. So make sure you're paying attention to the handedness of your application. Certainly some of them are different. So these are our different matrices. If you were doing this in code, most of the trigonometric functions specify the angle not in degrees but in radians. So if you're going to write this in code, make sure you convert degrees to radians as appropriate. Now we can take a look at this inside of Houdini. So I have a lovely torus here, and again it's got these lovely different handles that we could use to manually rotate. And I could grab each one of these red, green, and blue circles, and I can actually rotate the object. And when I do that, it's going to manipulate the rotation field here. If I want to be more precise, I can just type the number of degrees that I want to rotate by into these boxes, and it will rotate by that amount. You don't have to specify the radians here. Radians is not something most humans remember. They think about rotation in terms of degrees. So you just have to do degrees here. So if I want to rotate, say, around the x-axis by 45 degrees, I can type 45 and it will rotate here. And we can open up Houdini here and we can do that. So I'm going to switch to our rotation handles. And you can see here I have a red circle, a green circle, and a blue circle. And if I grab one, it causes the rotation. Just like that. I didn't actually want to do that rotation. So we're going to switch it back to zeros here. There we go. Now, there's a couple things you should know about rotations. If we were doing rotations like this, there's a little problem we can come across. It's called gimbal lock. What ends up happening is we rotate one of the axes onto the other one. So it's like the y-axis collapses into the x-axis. And then what happens is we start rotating around the collapsed axis, except it just starts doing this weird jittery thing, and it's not what we expect, and it's because the axes have collapsed onto themselves. So matrix-based rotation doesn't tend to be used anymore. What we do tend to use in a lot of video games instead of the traditional matrix rotations is quaternions instead. We are not going to worry about quaternions here, because we're not going to have gimbal lock with our simple rendering. But if you'd like to know more, I'm happy to post something about quaternions for you. And I'll see if I can find you a cool video of gimbal lock happening, because it's really amusing to watch it happen. All right. Our third affine transformation that we are going to deal with is the scale translation, or the scale transform. And this one's really easy. All we want to do is we want to scale the point along the x, the y, or the z axis. So we take our identity matrix and we're going to set for the x scale, we'll put it here, the y scale here, and the z scale here. It's great, right? And then that's going to, of course, whatever your x component was of the point, it will multiply it by that. So let's just, instead of talking about it, let's just show you what it does. So I don't want to show the rotation one because that takes too much writing. So for the scale one, we're in homogeneous coordinates here. So we have x, and then we're going to multiply it by our lovely point. We end up with, so remember, we're doing this row times this column. We're doing the dot product, really. So we're going to end up with, if we do that, ax, by, cz1. Ta-da, your point is now scale. Now, the value for the scale factor, x, we might be thinking, well, it has to be greater than 1, right? Nope. If you want something to be bigger, then you would make the number greater than 1. And if you want it to be smaller, make it smaller than 1. So we can, I'll do that in Houdini in a minute. So here is my torus, and now I'm going to scale it on a particular direct axis. So I have scaled it along x, I've multiplied it by 2, and you can see we've just stretched it out like that. And you can have, of course, all kinds of fun. We can switch over here to the scale parameter. And I can scale them all from the center at the same time. That's the little purple one. Or I can do individual scale. So let's make a tall, skinny apple. You can see here that it's changing the scale, or a really flat apple, or we can do all kinds of things. Or we can also type it into the box as well. So there you go. We have the ability to rotate, translate, and scale. Now, are those all of the different transformations that you could perform on a 3D object? No, actually it's not. There's also this concept of shear, which is taking something and applying a shear along the x, or shear along the y, or a shear along the z axis. We don't tend to use shear, but it certainly exists, and some rendering applications will actually let you manipulate the shear as well. But we're not going to do that. All right. Now this is where things can get a little bit tricky. And that is, we need to make sure that all of the affine transformations are performed with respect to the origin, because that's how it works. All of those matrices are with respect to the origin. So we are translating with respect to the origin. We are rotating around the origin. What does the origin mean? The origin is 0, 0, 0, so the center. Now that's nice. It's fine for translations. For scales, it's reasonable. But what about rotations? What if I want to rotate not about the origin of, but about the center of the object? Because if this is my origin and this is my object over here, and I perform a rotation, I'm going to be rotating around the center like this. But all I wanted to do was this. So I want to be able to rotate about an arbitrary point in space. And if you want to do that, what you need to do is, before you rotate, you want to move your object to the center. Perform your rotation, and then move the object back. Now, in order to do this, you need to know how to move the object to the position, but also how to move it back. Now we know its position, how to move it to the center. We take the center point of the object, and we're just going to negate it. To do the inverse, it would be the negatives. So invert that. We can also invert the matrix itself. And when we're doing more sophisticated affine transforms or combinations of them, we'll actually do the inverted matrix. But that's how we would do one of these rotations or translations about a particular point. But it's really important you do this in the right order. So as we showed you at the very, very beginning, if you do any of this with respect to a point in 3 space, if you do these multiplications in the wrong order, it doesn't equal the right order. So if we want to do translation, rotation, scale, that's not equal to rotation, translation, scale. So we represent these just by their first letter. So the order that you want to do this in is SRT. Scale, rotate, translate. That's the multiplications. It actually ends up on a computer doing the translate, then the rotate, then the scale. It is not a commutative operation. That means that SRT is not STR, is not TSR, as we showed you at the very beginning. And this is really, really important, because if you're doing this in code and you do it in the wrong order, you're going to end up with your object in the wrong spot, and you don't want that to happen. Let me show you. So this is my torus, okay? My torus is not about the origin here, so this red dot is the actual origin. So the 0, 0, 0. So I've already moved my torus away from the origin. I've already rotated it somewhat. I've rotated it negative 45 degrees around the x-axis. Okay. So this is what happens when you do rotation before translation. Okay? Now let's see what happens if we do it the other way. So if I did the translation before rotation, you'll see that I rotated the object and then translated it and then I rotated it. So you can see here that the object is rotated and moved straight up. So there's the center there. So just going back, wrong direction. So In this one, where we did rotation before translation, the center of the object is no longer in the center of the object. The center of the object is now down at the origin, in this red dot. But when we did translation before rotation, the center of the object remained with the object instead of staying down below. This is really, really important. Now, you can actually manipulate this in Houdini, as you might have guessed. So when you've highlighted an object, you can actually go up here, and it says transformation order, and you can actually choose what order you want it done in case you wanted to do it in a different order, which you might have a very good reason for doing that for certain objects. For this particular object and all the objects that I have, I'm making the assumption that the 3D model has the center in the center of the object, and therefore I want this to be done in the proper traditional order, which is scale, rotate, translate. So we do that. But I could very easily change that if I wanted to. I'm not sure if that's a feature that's available in all tools, though admittedly I have not used Maya in a very long time, so that might be available in Maya. All right. So now that we've got the basics of dot product and matrix multiplication, we know about the affine transforms, we have a rough idea in our head of what's going on with ray tracing or ray casting. Are we ready to do the casting algorithm yet? No. There's some more we need to think about before we can talk about the actual ray casting algorithm itself. What we need to talk about is this concept of model space and world space. And I want to go back to this Houdini page for a minute, because you'll notice when I was talking about it, I said that the center of the model is what we want to do the rotation around. And the center of the model is very different from the center of the world. And in fact, looking at these examples here, the center of the model stays with the center of the model. Whereas in this case, the center of the model did not stay with it. We have different coordinate systems going on here. What we have is the world space, which is this grid you see here. And we're not modifying the world space. The world space, right now I'm not modifying. It's not to say that you can't modify the world space. It's just we're not going to do it. We've got y-axis going up, because we've got a left-handed coordinate system. I've got x-axis going towards the right, and z-axis coming out of the screen. Those are the positive axes. 0, 0, 0 is right here in the middle. That's going to stay there. But the model itself might have its 0, 0, 0 point somewhere else. When you download models off of the internet, so Turbo Squid, for example, you need to be very, very careful, because sometimes the free models, more often than not, have the center of the model space, which is where is its 0, 0, 0 point, not in the middle of the object. So there's a few different places it would be traditional to have the center of the model space. One of them would be the center of the object. That's a really nice place to have it. Another place that makes a lot of sense is the center at the bottom. And another place that kind of makes sense is the lower left corner. So those are the three kind of traditional places where you might see on a model the 0, 0, 0 element. So when you're applying a transformation, you have to make sure that you're applying them in the correct space. So if you apply a rotation to a model in world space, then the whole model will rotate around the world space's center point. Whereas if you apply a rotation in the model space, it's going to be just rotating the model about its center. So it's the difference between moving the object like this, and just moving it like this. And this is where the quality of your models that you find is going to come into play, because a lot of the free models have their model space center in a really bizarre place. And so that when you do the rotation, it's doing it about some weird point, and you're like, I'm confused. What's going on? Why is this not looking the way I want? And it's simply because the rotation is being performed about the model space center, and the model space center is in a really weird spot. I'll give you an example in a minute. And keep in mind, world and model space are two different things. The world space is the actual, where all the objects are living. A model space is the coordinate system for the individual model itself. And you want to be moving the models with respect to their own space, especially the rotations. So let's take a look at what I meant by a bad model. So this is a model I downloaded off of TurboSquid, which is really a great website for finding models, free ones, and ones that cost thousands of dollars. By the way, I don't anticipate that you're going to spend any money to purchase models in this course. I'm going to be providing you with asset files. You're welcome and in fact encouraged to add more asset files, but please don't spend money. There's many free assets out there. But as I said, do be careful. So I wanted to get some cool cut gemstone assets, because when you want to show certain properties of transparent materials, the cuts of a gemstone actually let you see some of the different interesting properties, like a total internal reflection and stuff like that. So I downloaded this package of, well, you can't even tell right here. I think there's like a total of 9 different gemstone shapes. And I imported it into Houdini, and I'm like, I can't see it. What's going on here? And then I zoomed out, and I zoomed out, and I zoomed out, and I zoomed out, and I zoomed out. And the reason why I couldn't see it is because they're huge. So the scale of the objects in their own space was massive. When I import it into Houdini, you can see here that it's negative, like they're lying somewhere in the negative space. So the negative z-axis, they're absolutely massive. They're like 600 and 700 units tall. And the other problem with them is the origin, the model space origin is not in the lower left corner, it's not in the center of the bottom, and it's not in the center of the different gems. It's way over here in the world space 000. Some applications or some individuals, when they're exporting these models as OBJ files, they get the world space saved with it. I don't know how this is happening because I'm not somebody who creates models. I mean, I did it for fun maybe 15, 20 years ago, but I have not done this in a really long time. But they ended up with their world space 000 as being the model space 000. And the problem that you get that arises from this is that now if I want to translate this forward, because the 000 is not in line with the actual model, if I'm moving this 500 elements forward, I may not actually be moving the gems to the position I want, because the gems are not at this position here. They're further back. They're about 500 units behind it. So if I move this 500 units, I think I'm moving it over here, I'm actually only moving it to here. And if I rotate this, I'm not rotating these, I'm rotating about this point right here. Be careful. And remember that generally speaking, we are doing rotations about the model space's center, not the world space's center. Okay. Something else I want to point out when we're doing rotations. There's so many details about rotation. So I showed you that you can change the order of the transformations here, but right beside it, when it comes to rotations, you can actually choose the order by which we multiply the rotation matrices together. So the traditional order is this one here, X, Y, Z, but you could definitely do it in another order. The result is different because A times B is not equal to B times A. So that is why we have the ability to change the order here. So be very careful. Make sure you know exactly which way you want this object to be rotated. And I think that's why, I mean, you can be very precise and specify, oh, I want exactly 45 degrees here, but sometimes it's just easier to grab the handles and just drag it. So we know about model space, we know about world space. There's more spaces to know about. So when we are viewing the world through a camera, we're not just seeing this rectangular box. We're treating the eye, or the camera lens, as a singular point. And the lens is kind of curved, and so we're actually seeing like this cone into the world. And we call that the field of view. But when we're doing rendering and we have this, we're going to have this, instead of just this cone, we have this thing called a viewing frustum. And you can see it here. I actually forced Houdini to show me the view frustum here. So for this camera, I have a view frustum. So these diagonal lines coming out of the camera are showing you the range that you can see. So they're going out into the world from that point like this, along a particular field of view. And then we have something called the near clipping plane and the far clipping plane. And what these two planes are is any object that's in front of the near clipping plane is not going to be seen. It's going to be clipped. And anything behind the far clipping plane is also going to be clipped. So what you are actually rendering is anything that falls into this center volume here. Now we can actually play around with the camera a little bit. So I'm going to go over here and let's click on my camera. So I've got a lovely camera view open, and we can, and this is again Houdini. You can use Houdini if you want, you don't have to. So this is the camera properties for this camera node, and you'll see here we've got all kinds of things, regular camera properties. We can simulate many different kinds of cameras. Now the view frustum I just showed you was called a perspective one, but there's also different ones like orthographic and so on. Perspective is the one we want for now, and we can change the focal length. So I can show you this. So if I change my focal length, we would be changing the viewing frustum by adjusting this focal length. So it's going from really thin, wide. So that's what we're doing. We're opening it up. And it changes back to what I had it at, which was 50, which is a pretty default one. We also have the ability to set the cropping and the near plane, clipping plane and the far clipping plane. So if we change the near clipping plane, you see that? It's pretty neat, right? So what we're doing is we're saying anything that is in front of, between the camera and the near clipping plane gets chopped, which is why this funny table model looks all funny, is because we're literally chopping the table. So that is my near clipping plane. Let's change it to back to what it was. Keep pushing the enter key, which is not what I mean to do. And then the far clipping plane, which is the back, anything behind the far clipping plane is going to be clipped off. We're going to get rid of it. So let's adjust that so you can see how that actually behaves. It's going to take a while. Let's see there. So let's set it to just 5. Oh. The problem here is that because the far clipping plane is actually so far away, we're not even seeing our effects. So if I set it to 4, nothing, 3, nothing, let's set it to 2, 1, we got rid of those. Let's set it to 0.5, we got rid of some more stuff. So that is our far clipping plane. Let's set it back. So those are the different things that we can manipulate within this viewing frustum. So this is what the camera is actually going to see. Anything that's in this lovely little trapezoidal box, we call it the viewing frustum, that's what we're drawing. We're going to keep all of that stuff. So we call this, it's a part of a rectangular pyramid. And what we want to do is we want to be able to project those. If you look at this, this is not a nice rectangle. This is a funny stretched out rectangle. And yet the objects in it are going to be somewhat distorted. So when we adjust this focal length here, when we adjust it, we are changing how certain objects are rendered. Look at that. When I set the focal length, you see here that it's applying a distortion to the objects in the scene. Well, it is another space. This is the viewing space. And there is a matrix that we can do called the perspective view transform or projection matrix that is going to map the frustum to world space and world space to the viewing frustum. And we are going to do that so that the objects their points are actually going to be rendered appropriate to the camera. Now this is a much more complicated matrix than the ones before, but we have our field of view, theta. So we're going to represent that by an angle. We have the aspect ratio, which is the ratio of the width to the height of the image that we are rendering, or the view frustum. So in the case over here, you can see I have, this is a 720p image, but I could set this to, a HD TV, so a 16 by 9 or 21 by 10. There's lots of different ones you could set it to. So that's going to be our aspect ratio. And then we have the Z position of the near clipping plane and the Z position of the far clipping plane. So, and that we have as F and N. And this is our matrix here. Now, for those of you who are not familiar with cotangent, that's just the opposite. You flip it. Now, this is not usually a matrix you would actually see or use inside of something like Houdini. Certainly, you can manipulate it. But tools like OpenGL and DirectX, this would be a constant they have in their system where you say, give me the field of view and the near and far clipping planes you want to use and your image size, and we'll spit you out that matrix. You don't need to worry about it. Now, it's not the only way to do it. There are certainly many other approaches to do this transformation. And in fact, there are many other different kinds of transformations, because we've shown you the perspective view transform, the perspective view frustum. But there's other ones. For example, the orthographic view projection. Instead of having the rays go out like this, they're going into the world straight. And that means that you don't get the perspective. Everything, so the sphere that's in front looks the same size as the sphere that's in behind. It's orthographic. It appears flat, and there's no concept of perspective. It's a cool thing, but it's maybe you don't want to do it. Let's just look at it. So let's set this far away. And you can see here kind of that this apple in front is bigger than this apple in behind. And if we set this to orthographic, we get a very different view. And we can set it to, so there are some other ones. There's also a polar or a panoramic camera where you can actually see things like that. And obviously that one's going to give you a different view transform. And there's also cylindrical panoramic. In this case, we're not getting an effect because I haven't changed the other parameters. Traditionally, though, we're going to use the perspective. There we go. There's our perspective view transform. All right. So each of those different kinds of projections are going to have a different matrix to perform that conversion. And I'm sure if you look in your favorite graphics textbook, which this is my favorite graphics textbook, they will actually list all of the different view projection matrices that you could use. Another one that's very simple is if your camera is positioned at the origin and it's not rotated, then you can actually compute and you've got an image plane. There's a really simple way to compute the world space position of pixel P, because the image is the image plane, and even it has its own coordinate system, because an image only has an X and a Y. So, and 0, 0 is always the bottom corner of the image or the top corner of the image. So we have to translate those pixel positions into the world space so that we can fire the rays through them, which is what we're going to have to do in our ray tracer. And so this is, in the simplest case, a matrix that you can use in order to do that. So you simply are going to do some translations to move the center, or the origin of the image, to the center of the image. And then we're going to apply this other position here, which is moving the camera back from the image plane so that we can make sure we have the correct field of view. But this only works if your camera is located at the origin and it's not rotated. So your camera is looking in the same direction. So the camera's axes are identical to the world space axes. So positive is the same, negative is the same for X, Y, and Z. And then this lovely matrix here will work for you. All right, so the next thing that we need to talk about, we're still not at the point where we can show you the raycasting algorithm. We have, I keep saying rays. What is a ray? Well, we are using the term ray to represent a beam of light. And our beams of light have an origin and a direction. So when we're talking about rays, we typically represent them as depending on your system, as an origin and a direction, or sometimes just a direction vector if they're coming from, say, the center of the world space. So we have our origin and our direction. And our direction vector is going to be normalized. That means it's going to have length 1. And if you remember from the beginning of this lecture, we showed you very quickly how to actually perform that normalization. But it must have a normalized direction vector in order to be used in the different computations. Now these rays are used to simulate the light rays in reverse for us, because we're doing ray casting, which goes backwards. So we're coming from the eye and going through the pixel and into the world. In a lot of ways, you could actually consider these rays as queries, because what we're going to do is use the ray to ask the question, do I see anything from this pixel? And then from when we talk about ray tracing, once we've found our surface point that we've intersected, we then use the ray to ask, can I see the light? So these rays, we're using them to simulate the path of light in reverse, but they're also queries. They're the questions. We're asking, can I see something with this ray? Does this ray intersect any objects? All right. We can now do the basic raycasting algorithm. So for every pixel in an image, and images, of course, are made up of lots of pixels. Oh, my battery died, so I guess I can't draw except with a mouse. So for our image, for each one of these little pixels here, for each pixel, I am going to create a ray whose origin is the camera, and it passes through that particular pixel. And I'm going to figure out which object that ray intersects, if any. Now, it is possible that that ray is going to intersect several objects. And it's not, I don't want to know about every object that the ray intersects. I want to know which one does it intersect closest to the camera. And once I know if it intersects an object, I'm going to compute the final color of the pixel, which in the case of raycasting is just what is the color of the object. So if it is a white dragon, it would be a white pixel. If it is a red flower, then the pixel would be just red. We are not doing any lighting computations whatsoever. All right. So let's go into a little greater detail here for each of these steps. So the origin of the ray is O, and that is the position of our camera. Now typically for our scene, we would place the camera at some point 0, 0, so 0 along X, 0 along Y, and then some distance away from the actual screen, because we want our scene to be actually in view. And you could, if you wanted, put the camera at 0, 0, 0, and then push your scene back, all your objects back into the world so that they can be visible to the camera. Now, the direction of the ray really gets determined from which pixel it's going through. So the direction of the ray going through this pixel is different from the direction of the ray going in this pixel. They're all going this way, but which exact direction is a little bit different. So the way that we figure out the direction for our ray is we take our pixel position that we're sending the ray through, and we convert the pixel position to, which is in image space, to a world space position using a perspective view transfer matrix, such as the one that we gave on one of the previous slides. And you can use the simplified one, or you could use the more complicated one. That's up to you. Well, that's up to the situation. Once we have figured out the world space position of that pixel P, then we actually need to compute the direction vector. So we are going to subtract the origin from that position, and then we normalize that. So we have now a unit length direction vector. And so now we actually have our ray then, which is an origin and the direction. So that's step 1. Step 2. We need to test for intersections. We need to know what object is going, this ray is going to intersect. Now, so what we're going to do is for every model in the scene, we need to check if that ray intersects with the model. Now, sometimes this can be a little complicated because the model typically has the vertices of each of its little components given in model space coordinates, but our ray is in world space coordinates. So what we need to do is either put the model, translate it to world space, or translate the ray into model space. You can do either one. I have a tendency, because I don't tend to do animations, I tend to take my models after I'm done creating my scene and do what I call flattening them, which is I convert them to world space so that I don't have to do this for each ray. It's just going to cut down on the computations for my specific case. So I'm going to do all that flattening beforehand. Otherwise, the ray is going to have to be transformed into the model coordinates or the model into our coordinates. Probably it's going to be cheaper to translate the ray into the model if we're going to be doing this for each ray for every object. And what that means is whatever transforms we have applied to the model, we're going to have to apply to the ray. And then once we have transformed our ray into the model space coordinate system, or vice versa, then what we can do is check if that ray intersects that object. Now, what does that mean? Depends on the object, but we're going to deal with that in a minute. As I said before, just a brief reminder, you might intersect many things. So if this is the ray origin and these are all of the different objects, we might intersect many objects. And what's interesting is you might intersect many objects more than once. So if we have the conversation about intersecting spheres, there are 2 ways that you can intersect a sphere. I do not have any spherical objects. One way you can intersect a sphere, well, I guess I have this T. Let's pretend this is a ball. So one way that you can intersect it is a tangent. So you touch the sphere only at one point as you're brushing by it. But the other option, more often than not, is that you intersect the sphere twice because the ray actually pierces through the sphere, as it does with all three of the spheres on the screen right now, the red, the yellow, and the blue one. So we have 6 possible intersection points, but I don't want all 6. I want the one that is visible to the camera, which means I want this one right here because it's closest. So I'm going to, as I'm testing the ray for intersections, you might be like, oh, I intersected something, let's stop testing. But you can't, because you don't know at that point if there's any other intersections which might be closer to the camera. So what we want to do is we collect all these intersections up, and as we collect, when we say, okay, I've got an intersection point, it is at this position away from the camera. And then I get another intersection point, and I ask, is it closer to the camera or further away? If it's further away, I throw it out. If it's closer, I throw the old one out. So we want to keep the one that is at minimum distance from the camera. So we're keeping the nearest one and throwing out all of the others because they're hidden. We don't care. Now, to compute the final color, we'll come back to intersections in a minute. To compute the final color of the pixel, whichever object that nearest point belonged to, it's going to have a material associated with it. So for example, if I go into Houdini here, you can clearly see that these different apples have different colors. Okay, they're all gold, but they're different looking golds. This table has a different color. These walls have a different color. In fact, Houdini has this whole lovely material palette where I can actually manipulate these different materials, and I can make my own materials even. So every object is going to have a material associated with it. And most materials have a base color or diffuse color. And when we're doing ray casting, that's the color we want. So we are going to set the color of that pixel to the base or diffuse color of the object that was closest to the camera for that ray pixel. We are not doing any computation of shadows, reflections, or lighting. We are just doing a visibility check. All right. We do need to go back and talk about intersections, because this we're going to be doing a lot of. Now, this is obviously something that is hidden inside of tools like Houdini. They have a library, they just do this. There are many different kinds of objects that we could intersect. The simplest thing that we could intersect is actually a sphere. Because when we represent a sphere, we're not going to represent it as a bunch of vertices and edges and faces. A sphere is a center point and a radius. That's it. And actually, the ray object intersection test for this particular thing is very simple. But there are all different other kinds of objects. For example, we could go back to the dragon at the very beginning. This dragon is quite a few megabytes in size because it's thousands of vertices, and it's comprised of thousands of triangles. So if I wanted to do a ray object intersection with this dragon, I don't just say, hey, does this ray intersect the dragon? Well, I don't have a magical formula I can use to check if the ray intersects a dragon. What I have to do is ask, does the ray intersect any of the triangles that make up the dragon? So if the dragon's made out of 10,000 triangles, which I think it is, then I don't do one ray triangle intersection. I do 10,000 ray triangle intersections. And the reason why you might be like, but what if you intersected one triangle? Couldn't you then say, yes, it intersected? For raycasting, technically speaking, yes. But also no. Because it depends on your scene. what if you have a mesh that goes around something else? And the first ray triangle intersection that you did was at the very back. That would never be seen. So if you just stopped there and said, oh, no, that wouldn't work. So you can't just stop with doing one ray triangle intersection in this case, because there might be multiple, some might be closer, there might be other objects dispersed in there. You've really got to do all of them. You might also, instead of being comprised of triangles, although we definitely prefer triangles, we might also have quads or quadrilaterals, so four-sided things, in which case we would have to do intersection tests for those. We're not going to worry about those. I don't like things that are made out of quads. I prefer things to be made out of triangles personally, because they're easier to work with. Not to say that, I mean, you can take a quad and just divide it into two and it makes two triangles, but I don't want to do that. So let's go back and just discuss this idea of a ray-sphere intersection. So we can define a sphere very simply as a center point P with ABC and a radius R. Then we have some ray Q with an origin O and a direction D. Now I want to know, does ray Q intersect S? Well, there's two different ways that it could intersect S, as I mentioned before. It could be a tangent to S, which means it just skims the edge of the sphere, touching the sphere only in one point. There's actually a second possibility. The camera might be inside a sphere. As odd as that might sound, you might be inside a big environment map projected as a sphere, and so if your ray is originating from inside of the sphere, then it could only possibly intersect one point. So, ray is inside the sphere, it will intersect one. It does happen. The other option is that the ray intersects the sphere in 2 points because it pierces through, in which case we need to identify both points and figure out which one is closest to the camera and throw the other one out. And then of course there is the third option, which is it doesn't intersect the sphere at all. So what we want to do is find out A, how many times does the ray intersect the sphere, and B, which of the intersection points is closest to the camera. Now what's really interesting is we can actually, and this is why we wanted the direction vector to be of length 1, is because the position where the ray intersects the sphere can be described using the following formula. It is the origin plus some scalar multiple t representing the distance times the direction. So if we were to draw this, and I know my pen died on me, if we were to actually draw this, horrible mouse drawing, here we come. So we have a origin, and here's our not so straight ray, and here is our intersection point here. Well, this is origin O plus, this is the direction, and it is t distance away from the origin. So there you go. The reason why the direction vector needs to be normalized or have unit length is so that we can compute the distance of points along the ray. And if your direction vector is normalized, unit length 1, you can do this. And if it's not, you can't do this. So that's how we can find, once we've determined the distance, we can find the actual surface point quite easily. So how do we do this? I'm not going to derive it. I'm just going to tell you the formulas to use, and you can use them. So the first thing we need to figure out is how many points of intersection there are between the ray and the sphere. And we can do that by solving this quadratic equation. And the number of roots that the quadratic equation has will tell us how many solutions there are. So we're going to make 3 variables, A, B, and C. And this is why we had to look up dot product at the very beginning, is because dot products come into play here. So A is the direction vector multiplied, or taking the dot product with itself. Then we have B, which is 2 times the direction vector taken as the dot product with the origin of the ray minus the center of the sphere. And then C is the origin of the ray minus the center of the sphere taken as a dot product with itself, and then subtracting the squared radius. How did we come up with this? We used parametric equation of the sphere and the ray, and we are solving for t, which is t is the unknown. T is the point on the ray that the sphere intersects. So we're trying to solve for t. So then we put the values a, b, and c into our quadratic equation, and we note that the number that sometimes you're not going to be able to solve this, because if b squared is less than 4ac, then the value under this root is going to be negative, which would yield a complex number. We're dealing with real numbers here, not complex numbers. So if the value under this root, called the discriminant, is less than 0, the ray does not intersect. So we're going to, this is a really nice test to see how many times we intersect. We compute a, b, and c, which is fairly straightforward, and then we check the value of b squared minus 4ac. If it's less than 0, no intersection, move on. If it's equal to 0, then the ray is a tangent, and if it's greater than 0, then the ray intersects at 1 or 2 points. So the ray is either inside, originating from inside the sphere, or the ray pierces the sphere. And then what we're going to do is, if the ray does intersect the sphere in 1 or 2 places, we solve the quadratic equation, and that is going to give us the value of t, which is the distance along the ray. If t is negative, we throw it out because it's behind the origin, going completely the other direction, and therefore it's not an intersection point. So we only want positive t because that would mean it is in front of the ray. Actually, in front of the origin. And then we can compute the surface point as the origin of the ray plus t times the direction vector. Okay. So we have a little example here, and I wanted to walk you through this very quickly because I think it's important to see it. So we have a ray that originates from the center and is pointing down the positive z-axis. So it's coming out of the screen and into your face, because why not? We have a sphere that has a center 0 and radius 1. So picture this. The ray is originating inside the sphere. So we know that the ray, mentally, because we can picture it, is going to pierce the sphere in exactly 1 spot. I can even tell you what it is off the top of my head. It's going to pierce it at 0, 0, 1. So, but let's pretend we don't know. So we compute a, b, and c. So there's a, taking the direction vector and taking the dot product with itself. We compute the b, and we compute the c component. Then we're going to compute d, which is the value of the discriminant. And we find that the discriminant is a positive value, which if we go back to this table here, that means that the ray intersects at either 1 or 2 points. Yay. That means we can solve the quadratic equation. So we solve it. So negative b plus the square root of 4 over 2a, or negative b minus the square root of 4 over 2a. So that is going to give us either negative 1 or positive 1. Now we know that if the value is negative, that it's not a correct value for t because it's behind the origin of the ray. So we can toss this one. This one, put a big X through it. It's not a valid intersection point. But this root, we got a solution of positive 1, which means this one is a value of t where the ray is intersecting the sphere. We take this value of t equal to 1, and I substitute it into our equation. We get as the origin of the ray plus t times the direction of the ray, and I get the surface point as 0, 0, 1. So ray-sphere intersections are actually blissfully simple. And on your assignment 1, we're only going to have ray-sphere intersections. I decided to keep it very simple. We're not going to do ray triangles or ray quadrilaters. It's just ray spheres. Now, how do we do ray triangle intersections? Obviously, this is going to be a lot more complicated. A triangle is not defined as a point and a radius. A triangle has 3 vertices, A, B, and C. And what's interesting is those 3 vertices lie on some plane. Let's pretend this is our plane. So our triangle creates some plane in 3 space. And what we're asking is, does the ray intersect not only the plane, but does it intersect the triangle that lies on the plane? And there's different ways that the ray could intersect it. The ray might not intersect it, obviously, because we might have, this is the triangle, and this is the ray. They are parallel to each other. They will never touch. Okay, fine, whatever. Or the ray origin might be up here, and the ray might go like this. Not parallel, but not intersecting either. So there's also the possibility that the ray pierces the triangle. If it pierces the triangle, it will intersect it in exactly 1 spot. There's also the possibility of there being an infinite number of points of intersection, and that is if the ray lies on the plane and on the triangle, which means there's an infinite number of intersection points because it is tangent to it. Potentially an infinite number of points. So, computing this is a little bit harder. The first thing that we need to do is to compute the normal of the plane. We need to determine, does the ray intersect the plane? So in order to do that, we need to know the normal of the plane. In order to compute the normal of the plane, you need 2 vectors on the plane. Good news. We have 3 points in a triangle, so we can compute 2 vectors on the plane. So we are going to compute the normal as the cross product of 2 vectors. And here I just said b minus a and b minus c as our 2 vectors. So we do the cross product of that. That gives us the normal. Now, before we use this normal, something that's not written here, please make sure you actually normalize it so that it has length 1. Whenever you make a vector, make sure it has unit length. That's a critical step here. Then what we're going to do is we're going to solve for t, which is going to identify the point where the Q, our ray, intersects the plane. So we're not testing the triangle right now. Right now we're testing, does the ray intersect the plane? So here's the issue that we might have. D, which is the direction vector of the direction vector of the ray, dot product with the normal might equal 0. Which may mean it doesn't intersect. So if the denominator, it's the bottom, is 0, then there is no intersection. You may be like, how could that be possible? Well, if I have the direction vector as 1, 0, 0, and the normal as 0, 0, 1, the dot product of those 2 things is 0. So there's no intersections. If, however, the denominator is not 0, then Q intersects the plane at the point origin plus t times d. So this was computing t. So now we know where on the ray the plane is intersected. Now, if t is negative, then we throw it out because it's behind. So that's the other thing to keep track of. The next thing that we're going to do, now that we've determined that the ray intersects the plane, now we need to know, does the ray intersect the triangle? And there's lots of different techniques that we can use to determine if the ray intersects the triangle. One of them is to identify the barycentric coordinates of the intersection point. And we're not going to get into details as to what that is, but this is the formula that we would use to do it. So we have the points of the triangle A, B, and C again, and O, the origin of the ray. And we want to solve for beta and gamma. Okay? So what we're trying to determine is there a value for beta and gamma such that the triangle is actually being intersected? And we will know this is true if beta is greater than 0, gamma is greater than 0, and beta plus gamma is less than 1. If this holds for the values we find for here, then we intersect the triangle. Okay? Now keep in mind, I know there's a lot of letters here and there's no numbers. We know the values of everything but beta and gamma. So we can figure out everything else from there, because what we would have is A minus B times beta plus A minus C times gamma plus D times T equals the first component of A. So you end up getting a system of equations, which we would then use a linear solver for. Ray triangle intersection is very expensive, by the way. Definitely more expensive than doing ray sphere intersection. All right. So we've got a good picture of the algorithm for ray casting. We've got a good idea as to how to do ray object intersections. We also have a good idea about the different transforms that can happen. We've got world space, model space, view space, image space, and we kind of have a good idea as to how to move between each of those. We know the importance of rotating about the correct origin, the model origin versus the world space origin. But let's talk now more about ray casting in general. So what do we use it for? Obviously, as I've mentioned, it's the first part of ray tracing. Before we can figure out how pretty a pixel should look, we need to know if we intersect any objects. So this is the very first step to our ray tracer. It's just the visibility test. What am I seeing? So raycasting is used for a number of purposes, as we've already mentioned. One, of course, being just a visibility check. Like, what can I see through this pixel? And that actually has a number of very interesting roles. So one of the things that you might be doing is trying to figure out, is the scene I'm trying to set up, does it make sense? Am I seeing what I want to see in front of the camera? Are the colors roughly where they're going to need to be, and so on and so forth. And so raycasting can be a really cheap way of helping you get a good sense of what your scene is going to look like. And just to give you kind of an example, so I'm going to open Houdini up here. So I have this this image here that I've been just tinkering around with briefly. And in this image, this is actually a ray traced image. There's a number of very computationally expensive operations going on. For one, we have reflections. We also have transparent materials, so they are going to refract light. We also have soft shadows, we have environment lights, and a number of other things that are going on. And all of these things are very expensive. This image here took almost 4 hours to draw on a pretty decently powered computer. Now, when I was laying this scene out, I needed a way of knowing, before I did this 4-hour render, are these apples in the right spot? Are these candlesticks in the right spot? Am I getting the right look and feel for the image without the final color? And that's where raycasting can come in handy, because it's a cheaper way of rendering your scene so that you get a good sense of what things are going to look like. And a lot of these tools, like Houdini, do give you a somewhat simplistic view with wireframes and really, really rough versions of the materials. And that's an alternative approach to just a quick visualization of your scene, but raycasting is another one. And in fact, when I wrote my original ray tracer 16 or 17 years ago, a long time ago, I actually used raycasting as part of the visualization process. So as you were adding elements to the scene, it would do a raycast so you can kind of get a good sense for the layout of the objects. So that's one thing. Another thing is this concept of visibility checking. It's making sure that items actually fall into the viewing frustum. And, you know, I want to say with tools like Houdini and Maya, this isn't really a big deal. You wouldn't really use raycasting for that, because if you go over to the scene view here, we're actually looking through the camera. They have that built in. This is not always been the case, and it is not always the case with all ray tracers. So there's another ray tracer called POV-Ray, which you've heard me mention in the previous lecture. It's the persistence of vision ray tracer, which is all kind of code-based. And the problem with a code-based ray tracer is you don't actually see what you're doing. You are kind of mentally picturing where each of the objects are going to lie. And so you would hit the go button, which is really just run this computer program, and then you might have to wait 6 hours to get the result. And that's kind of where raycasting can come in handy. It can be a fast render for these more code style ray tracers. Making sure that things lie in the camera and so on. Something else that the raycasting algorithm has been used for, or is used for, is this concept of picking. So when we have a 3D scene, I'm just going to go back into Houdini here to explain this. So you have this 3D scene, and I'm going to click on this so I'm in selection mode. So I want to select an object in this scene. How does Houdini know which of these objects in 3 space I'm actually selecting? Let me explain here. So I've got a back wall here and a separate back wall here. I've got these apples which are sitting in front of each other. Now this front apple here is actually occluding pieces of the 3 apples that are kind of above and behind it. How does Houdini know that when I put my mouse right here that I mean this apple and not the one behind it? And actually there's an algorithm you can use to determine this based off some of the ideas of raycasting. And the idea is you are sending a ray through the pixel of the screen into the program, and it's going to send that ray, and whatever object intersects that ray first is the object you are selecting. So you can actually use this idea of raycasting as a mechanism for selection in a 3D environment. So you can do that, for example, if you're in a video game and you mouse over something. Well, how do you know that you have moused over the candlestick that is in the background as opposed to the candlestick that's in the foreground? And the answer is because we're sending a ray to ask, okay, well, what object did you actually intersect? So that's one mechanism by which you can achieve that. So it's a very important algorithm. And of course, the other thing is that this is the basis for ray tracing. So ray tracing, which we are going to actually build on top of this, is going to take these ideas and expand them. But this first algorithm will always be the first part of the actual ray tracing algorithm. Now, excuse me, there's something we should talk about, and I've kind of mentioned this a few minutes ago, and that was this concept that ray tracing is really expensive. Ray tracing is exceptionally expensive. What's interesting about it is the algorithms for ray tracing have actually been around for 40 or so years. And we've had access in the film industry to these kinds of algorithms, but for rendering animated films. And yet the actual ray tracing doesn't really get used for video games, and it doesn't really get used for rendering animated films or VFX until fairly recently. And the reason for that is because it's incredibly expensive. So I'd like to talk about the cost for raycasting, and we're going to continue this discussion of the cost of these algorithms when we talk about ray tracing, and this is going to be a recurrent theme. And the reason for that is if you're doing any kind of rendering with Maya or Houdini, and you're trying to decide between should I be using real ray tracing or OpenGL's approximation using shaders, you need to understand not just the visual differences between the two techniques of rendering, but you should also be very aware of the cost differences. The truth is, doing ray tracing and global illumination are going to give you significantly more realistic results. The lighting will just look more real. The colors will be richer and deeper. But it comes at a pretty big cost, as we're going to see. So how do we compute this cost? So when we're trying to compute the cost of an operation, we're usually asking, how many instructions would the computer actually be performing? We're not going to go that low level. When we're talking about the cost of something like ray tracing or ray casting, we always do it with respect to the number of ray object intersection tests you are performing. We're making the assumption that a ray object intersection test it's like a single operation. It's many, but it's essentially one in the grand scheme of things. So now when I say ray object, I'm not meaning ray mesh. The reason why we're not saying ray mesh is because if you look at the meshes of these candles here, and you can kind of see this is a wireframe of it. This is printing out the quads, instead of the triangles. But you can see here that there's probably thousands of them. When I try to do an intersection test with this object, I don't have a magical formula that says this is the formula of a candle. There's no formula for a candle stick holder. Or if you have a model of a face, there's no formula for a face. What we're doing, and you might recall from previous courses, is you're taking the object and you are triangulating it. So you're turning it into a whole bunch of either triangles or quadrilaterals, so little squares and things. And when you were trying to do a ray object intersection test with that mesh, you're not just doing it with one thing. You actually have to test that ray with every single triangle in the entire mesh. So when we're talking about ray object intersections, we mean ray and simplest object intersections. So a sphere, a triangle, or a quadrilateral. So the very basic things. And when we're talking about the performance of these algorithms, it's how many of those operations would we expect to perform. So the one thing that we know is that our image has a width and a height. And we're actually going to send a ray through each and every single one of those pixels because we want to compute the color for each and every single one of those pixels. So we can say that the image has a width W and it has a height H. And I know that I am sending a ray through every single one of them, which means the total number of rays that I would send for ray casting is W times H, the width times the height. So just to give you an idea of the number of rays you might send for a 1080p image, you would have 1920 times 1080, which gives you 2,073,600 rays for an HD image. And these days, I want to say an HD image isn't good enough and we need to do a 4K image, in which case that would be 4 times that. So we'd be looking at about 8.4 million rays that we would be sending. But for each of those rays, we need to ask every single triangle, quadrilateral, and sphere in the scene if the ray intersects them. So if we've got some big candlestick mesh like this, that I think has something like 10,000 triangles in it, that means every single ray is going to have to perform a ray triangle intersection test with every single one of these 10,000 triangles. So we get this cost of the width of the image times the height of the image, which gives us the number of rays, and each ray has to do an intersection test with every object in the scene. And if there are n of those in the scene, then the cost, or the number of ray object intersections, is W times H times N. And if you're ever reading some papers about rendering or ray tracing, you might actually see the costs written in a very peculiar way, and that is this O of WHN, or theta of WHN. And this is just effectively saying, what is the behavior of this as these numbers approach infinity? But I'm going to use this notation to refer to the costs in the future. So you might be like, that doesn't seem so bad. Computers are really fast. They can do billions of operations in a minute or a second. How much time is this actually going to take? Well, this image here took 4 hours. And when I was doing it, I turned on some optimizations, which we will talk about in our next lecture, because it's important to know that there are ways that you can speed this up. And if I remember, I always forget where this is in Houdini, but there is a button in here. Oh yeah, so it's images. Well, we'll find it tomorrow. There's a place in here anyways where you can actually turn on different optimizations. Oh, there it is. It's under rendering render for the mantra node. And you'll see here ray tracing accelerator, and there are some different techniques that you can use here. They have something called a KD tree and something called a bounding volume hierarchy. And we'll talk about these in our next lecture, actually, because it's important to know that you have options to improve the performance. But right now we're just talking about the raw, unoptimized version of this algorithm. All right. So this image took 4 hours. This image actually, and you might be like, oh, well, maybe it's really complicated. This is a really simple image. Really, really simple. There are 6, 10, 11, 12, 13, 14. There's 14 objects in this scene. There is less than 1 million triangles in this scene. And the problem that we come up against is that if you were trying to raycast a very basic scene from a movie, you wouldn't be looking at less than 1 million triangles. You'd be looking at millions of triangles. So I did a little computation here just to give you an idea of how long something like this could take just for the raycasting component. If we had a 1080p image, so let's bring up I'll bring up a little window here so that we can do some typing. So if we have a 1920 by 1080p image, so that's our W and our H, and we have, let's say, just 1 million objects in the scene. Okay, that is going to give us, I'm going to type this number here. And this is given in scientific notation. That's giving us 2.0736 times 10 to the power of 12. It's significantly more than 1 billion operations. Now, that's telling us how many ray object intersection tests are being performed. But what it's not telling us is how long that's actually going to take on your computer. Now, I can't tell you exactly how long that's going to take on your computer in any meaningful way because every single one of us has a completely different computer. Our computers are all running a variety of different tools while we're doing our algorithm, and that is going to impact the exact amount of time. But let's assume, just for the sake of this little brief discussion, that each one of these ray object intersection tests takes 1 microsecond. So it's like the millionth of a second. If that was the case, this would take 24 days. Yep. It's pretty bad. If instead of that, it took 1 millisecond, it would take 65 years to do it. That's very expensive. The point I'm trying to make here is that ray tracing and ray casting are very, very expensive. And to give you an idea, you're like, but that's just your basic computations. You haven't optimized anything. But what about Pixar? What about Weta? They have big render farms. How long does it take them to do this? Wow. So some of you might remember a film called Monsters University, which was released, quite a few years ago. I'm not quite sure. 2013. Oh, wow. That's actually quite a long time ago. For some reason, I thought it was a bit newer than that. So that movie actually had ray tracing involved in it because they wanted to create some more realistic lighting. And they did a very good job of it, especially for the time. And one single frame of that movie, as far as I've heard, took between 20 and 30 hours to render. Okay. One frame took between 20 and 30 hours to render on a render farm. And I have been to Pixar's render farm. It is big and it is quite powerful. To give you an idea then of how long it would take for a movie to render 1 minute of footage, so you would have, so there are 60 seconds in a minute. We typically do films at 24 frames per second, so 60 times 24. And let's take the average of 25 hours per frame. And that means that a minute of footage could take 36,000 hours. Now, obviously, that's not how long that movie actually took to render one minute of footage, because that would be 1 minute of footage was rendered every 4 years. When they gave out that number, it wasn't clear if that was utilizing the entire render farm or just one machine in the render farm. It's not very clear how exact that specification is. The point I'm making, though, is that even a specialized computer like that takes a really long time. That movie took a long time to render. If you tried to render a frame of that on your computer, it would take thousands of years. Or at least that's the computation I've heard. So these algorithms are very, very expensive. And this is actually one of the reasons why you don't see ray tracing and ray casting used in a lot of films and video games until very recently. Because in recent times, we've actually found a lot of tricks that we can use to get the look and feel of this and even perform some of these operations, but do it now in real time. or do it sufficiently well that and in a sufficiently small amount of time that we're happy to now do it. And we are seeing more movies using ray tracing, and we are seeing games use it as well. I think there is even a mod for Zelda Breath of the Wild where you can actually have it ray traced, which is pretty cool. Actually, not to say that it looks better, because it was not designed to be ray traced, so they don't have the right kind of lighting, and they haven't taken that into consideration, but it's totally possible. We will talk about how do you speed it up, just not today. So be very wary when you are doing a render job on your machine. Keep it in the back of your mind that this is going to be expensive. It's going to take a long time. You might try to do a simple image like this, and this image is not 1080p. This is 720. It's just the default camera in Houdini is a 720p camera. And I didn't bother to change it because I didn't want to be waiting for this image for the next 2 days. So when you are working on some of the assignments, so the first assignment, you are going to be implementing some parts of your own ray tracer. We're rendering simple enough things that you're not going to be having to wait for more than a minute or two to draw your scene. But in some of the other assignments, you're going to be asked to render some very specific things in tools like Houdini or Maya. And I want to let you know sufficiently far in advance that it's going to take a while. So don't leave it to the last minute, because there is the potential for a couple of these images to take half a day. Now, you don't have to sit there and watch it. That would be like watching paint dry. But your computer's going to be pretty busy for quite a while. And to that end, if you do need some machines to help you with the rendering, we do have remote access to the machines in the lab if you need them for those rendering jobs. So let me know and we can get you access to those if needed. All right. So that's the end of our discussion on raycasting. The ideas from raycasting are going to keep coming back and back and back. Along with this review of math, those ideas are going to be pervasive throughout the course. I've left a few review questions here at the very end, and I'm not going to go through these. Think about these, and then if you want to discuss your answers, by all means, we can talk about them in a live chat sometime. So that's it for today. In our next lecture, we're going to be talking about ray tracing, which is where we are going to take this boring image that we raycast and now give it some actual shape. We're going to actually look at how do you perform these lighting equations, how do we get shadows, how do we get reflections, and so on and so forth. And we're also going to look at a few techniques that you will have available to you in various tools like Houdini and Maya to improve the performance of these operations. So we will see you next week.